So in the previous video, we were looking for non-trivial automorphisms of a group, and we have already seen that in a special class of abelian groups, we can in fact find non-trivial automorphisms in a somewhat quite straightforward and easy manner. Let us recall that if G is an abelian group which has an element x naught which is not equal to its own inverse, then this mapping T, which maps every element of G onto its inverse, is a non-trivial automorphism of G. But this is when G is an abelian group and such an element exists in G. The next thing we are now going to do is we want to find some non-trivial automorphism of a non-abelian group. So we are now going to look at some special types of automorphisms known as inner automorphisms, and this we are going to do in any group, and then we will see how they can give us non-trivial automorphism when the group is non-abelian. So let us go through the details of that. So we start by considering any group. Let G be a group for any element in G we are going to define a mapping Tg from G into G by this formula. Tg maps a group element X into the element G inverse Xg. Okay. Now clearly Tg is well defined by the fact that the binary operation in G satisfies closure property. So this is again an element in G, and because the binary operation is itself a well defined map, so for a given X this element is unique. So that's why Tg is well defined. Let us just mention that also. Clearly Tg is well defined. Okay. Now the first thing we note about Tg is that Tg is 1 to 1. Let X and Y be elements in G such that Xtg is equal to Ytg. This implies G inverse Xg, which is Xtg, is equal to G inverse Yg. Now on this equation we can apply the cancellation laws. So by the cancellation laws, we have both the cancellation laws have to be applied to get this conclusion: X equal to Y. Thus this is 1 to 1. The next observation is that Tg, besides being one-to-one or injective, is also onto. It is a surjective mapping also. Note that for any element Z in G, there exists this element Gz, G inverse in G, such that, let us look at what Tg does to this element. By the definition of Tg, G inverse Gz, G inverse G, which you can clearly see is equal to Z. So that means any element in G appears as the image of some element in G under the map Tg. So Tg is onto. This implies Tg is onto. So Tg is a bijection, it's a bijective mapping on G. Now the next observation about Tg is the most important one, that Tg actually is a homomorphism of G. Also, what happens when we apply Tg on the product xy of the group elements x and y? Here we assumed x and y such that this equality is true. That part is over. Okay. So here again x and y are some elements in G, not just these elements. Or if this seems confusing to you, you can take some other elements also. Also, for say alpha and beta in G, we have alpha beta Tg equal to, by the definition of Tg, this is G inverse alpha beta G. Now note carefully that this last element can also be written like this: G inverse alpha G, G inverse beta G, because this G and G inverse, they will cancel each other in the sense that their product will be identity which will vanish, and this is nothing but alpha Tg and the other one is beta Tg. So Tg is a homomorphism. So that means Tg is a bijective homomorphism of G, so it's an automorphism of G. Thus, Tg is an automorphism of G, that is, Tg belongs to the group of automorphisms of G. This type of automorphisms are called inner automorphisms. Tg is called the inner automorphism of G corresponding to small g. I think that is how it's named. Yes. Corresponding to small g. I need ink. Give me a moment. Okay. Corresponding to G. Now, how can we use this type of automorphisms to show that if G is abelian, if our original group is abelian, then there is a non-trivial automorphism. To see that, you observe this. Now, suppose G is non-abelian. Did I say abelian just now? Non-abelian. Then there exist elements A and B in G which do not commute. The reason for non-abelianness such that AB is not equal to BA. Okay. Thus, now what happens if we apply the inner automorphism TB corresponding to the group element B? Also we will have an inner automorphism TB. If we apply that to the element A, what do we get? By the definition of TB, this is B inverse AB, and that is not equal to A. Why? Because if B inverse AB is equal to A, then AB will be equal to BA, which is not true. So what does this tell us? This tells us that the map TB changes some element. It does not keep every element constant. In other words, TB is not the identity map. Which implies TB is not equal to identity, and that's why TB is a non-trivial automorphism of G. So that's how, if we have a non-abelian group, then among the inner automorphisms we will get a non-trivial automorphism. That is TB is a non-trivial automorphism of G. Okay. Now we are going to investigate a little about the collection of all inner automorphisms. let I of G denote the set of all inner automorphisms of G. It belongs to AG, that we already know, where G varies over G. Okay, we can say quite a few things about this set. The first thing is this. The first thing is we are now going to show that this is a group. It's in fact a subgroup of A of G, the subgroup of the automorphism group of G. So let G, H and what can we take? Say K belong to G. Then what happens when we apply the composition of these two automorphisms, TG, two inner automorphisms, TG and TH, on the group element K? Note that because these are automorphisms after all, so they can be combined using the binary operation that we have in this group, which is nothing but function composition. So this is again such a function. In fact, this is again an automorphism, and that is because this is a group and these two are elements here. So by closure property, this is again an automorphism. We are applying this on the group element K. By the definition of function composition, this is equal to this. Now KTG is, by definition of TG, G inverse KG. And this again, by the definition of TH, is H inverse G inverse KG H, which is equal to H inverse G inverse K GH, where we have used the associative law in whatever way we want. Now this is equal to GH whole inverse K GH, which, if you look at the structure of this element, is equal to KTGH. Okay, now look at this equation. Look at the first term and the second term. The last term in this series of equalities. This case, since it's any element in G, tells us that as mappings, TG composition TH and TGH are equal. So TG composition TH is equal to TGH. Now TGH, because G and H are group elements, so their composition, their product in the original group G is again a group element, so this TGH is an inner automorphism. So what have we proved here? We have proved here that IG is closed under the function composition, under the binary operation in AG. Okay, so we have one of the conditions here for IG to be a subgroup of AG. Next, what happens when we apply? Oh, okay. For this, what do we need to do? The next thing we want to show is that the inverse of Tg as an element in this group is also an inner automorphism. Okay, so for that, let what should we use to denote this? Let us call it L. Let L be the Tg, sorry, this. Does it make sense? L is the image of K under the map Tg inverse. What is Tg inverse? You see, Tg is after all in AG, and AG is a group, so it's in that group. Tg inverse is the inverse of Tg in that group, and we already know what it is. It's nothing but the inverse of the function Tg. Okay, so the image we are denoting it by K, L. Then shall I get anything from this, or will it be better? Oh yes, I think that okay, not like this. Although if someone wants, one can cross it like this also, but there is a better way to get what we want to get now. Next, Ki, where I is the identity automorphism of G. Ki is equal to K. Now K can be written as E inverse K E, because E is the identity, which is nothing but T E, K T E, and that is equal to K. Now in place of E we can write G inverse, because in the group capital G, G inverse is E. And by what we have proved just now, this equation, if we apply it on in this special situation, we get TG inverse. So just like this one, where K is any element in the group, here also K is any element. So the map I and the composition TG inverse have the same effect on every element of the group. So as mappings they are equal. Thus I is equal to TG inverse. Now this is an equation where this is an equation in the automorphism group. It's an equation like this: identity is equal to xy. In a group, the form of this equation is like this. So when you have this in a group, what can you say? You can say that y is equal to x inverse. So here also we can say that Tg is inverse is equal to the inverse of Tg. So which implies Tg inverse. This is the inverse of Tg as an element of the group Ag, or in reality this is nothing but the inverse of the function Tg as a function, because Tg is a bijection, it will have an inverse function. This is that inverse function. So this is equal to Tg inverse. So the inverse of Tg is again an inner automorphism, namely the inner automorphism corresponding to the group element G inverse. So this belongs to I of G. So I of G is not only closed under the binary operation of Ag, but the inverse of every element in Ig is also in Ig. Thus, this is a subgroup of Ag, the subgroup of all inner automorphisms of G. Okay, now we are not done. We can say even more about this whole situation. We are now going to define a map and this Ig, we know what it is. It is the collection of all inner automorphisms of G, and it turns out to be a subgroup of G, and hence it's a group in its own right, but it has a name, and that name is natural enough. Ig is usually called the group of all inner automorphisms of G. Okay, fine. So the inner automorphisms form a subgroup in the automorphism group. Now next, let us define a map psi from G into automorphism group of G by defining the psi image of the group element G to be the inner automorphism corresponding to G. Okay. Now, first of all, this map is well defined. Why? Because for every group element, the inner automorphism Tg is after all an automorphism, and it's a unique one. For a given G, there is only one Tg. So this map is well defined. Psi is well defined, and G psi, the image of G under psi, which consists of all the outputs, is, you can clearly see it's nothing but the collection of all inner automorphisms. That is, this image is equal to this. Now our next aim is to show that this psi actually itself is a homomorphism. from this group into that group, into its automorphism group. So for that, let us take two elements G and H in G. Then this is almost obvious. Having shown this equation, now it's almost obvious. Then GH, the psi image of GH is by the definition of psi TGH, which according to this equation is TGTH. Don't forget that the binary operation that we now have between TG and TH is nothing but composition of mappings. That is the one we have here. And TG is the psi image of G, TH is the psi image of H. That is, psi is a homomorphism. We are now now we have psi as a homomorphism, and we know the image of psi. That is, psi is the mapping of G onto I of G. Now, what is the next natural thing to ask is, what is the kernel of psi? Because if we can find the kernel, then we can apply theorem 271. Let Z belonging to G be in the kernel of psi. So Z will be mapped by psi onto the identity element of this group, which is nothing but the identity automorphism. Then this is equal to, this is the consequence of Z being in the kernel of psi, and by the definition of psi, this is nothing but the inner automorphism TZ. Okay, so TZ is equal to the identity automorphism, which means what? Thus, for any element in the group, say gamma, I can't think of anything else, anything new. So for any gamma belonging to G, we have this. Gamma equal to gamma I, because that's what identity map does. It does not do anything actually, it does not change anything. That is equal to gamma TZ, and this by the definition of TZ, Z inverse gamma Z. Now this equation has a very nice consequence. This implies Z gamma is equal to gamma Z. Now gamma is any element in G. So our final equation says that Z commutes with gamma, that is, Z commutes with every element in the group, and that is why Z belongs to the center of the group. And so Z belongs to Z. Is the center of G. If you are following American English, it will be CENTER. Okay. Center of G. Is the converse true? Okay, so but before going to the converse, what have we shown here? We have taken Z to be any element in the kernel of psi. So that element has been shown to be in the center of G. So the kernel is contained in the center. Thus, the kernel of psi, which according to the notation for the kernel of a homomorphism is this, kernel of a group homomorphism. This is contained in Z. Conversely, if say Z prime belongs to Z, then for any gamma belonging to G, we have gamma Z equal to Z gamma. This implies, so here we are going in the other direction. Gamma equal to, in fact this gamma is equal to, let us write like that, otherwise it will be somewhat confusing. Z inverse gamma Z is equal to gamma, which implies gamma Tz is equal to gamma I, and this implies, or we should write it after this. We have this, and this is true for any gamma belonging to G. Thus, Tz is equal to I, but what is Tz? Tz is the psi image of Z. So Z belongs to the kernel of psi. Hence, the center of G is also contained in the kernel of psi. Now you combine these two inclusions. Therefore, the kernel of psi is equal to the center. So now psi is a homomorphism from G onto IG, where the kernel is Z. So we can now apply our isomorphism theorem and write the conclusion in the form of this lemma. Theorem 2, I hope I am remembering the number correctly. You understand what we are using here. If I made a mistake in the number, if it is not 271, please correct it. Theorem 271 now implies the following lemma. This is lemma 282. The group of inner automorphisms is isomorphic to the quotient group G by Z, where this is the group of all inner automorphisms of G, and this is the center of G. It's a nice result. The inner automorphism group turns out to be group theoretically nothing but the quotient G by Z. And keep in mind that our G is general, it may be a non-abelian group also. Still, Z being the center of G is normal in G, so the quotient G by Z makes sense. Okay, so next we look at this. Suppose phi is an So this discussion is over. Next we want to see what an automorphism of a group does to the order of an element. Let A be an element in G and let it have order I, where I is some positive integer. So we are assuming that A is an element in G that has finite order. We are not saying anything like all the elements of the group have finite order. That's not what we are saying. We have just taken one element in G which has some finite order I. Okay. Then to make it more clear, in bracket we write where I is a positive integer. Now we want to show that the image of A under phi, that is A phi, that also has finite order and its order is also equal to I. Since phi is a homomorphism, an automorphism is after all a homomorphism, so we have A phi to the power I. What is it? It is A phi like that I times A phi, and because phi is a homomorphism, this is equal to nothing but this, and I is the order of A, so this is identity, and phi is a homomorphism, so it maps the identity onto the identity. Okay, so we have got the equation that the ith power of A phi is identity. Now suppose there exists an integer j such that j is a positive integer, it's less than I, and the jth power of A phi is also equal to identity. then what do we get from this supposition? Then again, using the fact that phi is a homomorphism, we will then have this equal to now phi is 1 to 1 because it's an automorphism. Since phi is 1 to 1, this implies, this last equation implies this is equal to identity, and this cannot be true, because it will then violate the fact that I is the order of A, and hence the smallest positive integer for which a to the power I is identity. So there cannot be a smaller positive integer which will also enjoy that property. But this contradicts the hypothesis that I is the order of A. So the last supposition is wrong. What is the supposition? What was the supposition? That a smaller power where the exponent is smaller than I also makes this equation true. This equation, okay, the jth power of a phi is identity, which is not possible. That's what we have proved here. So that means just like I is the smallest integer, positive integer for which a to the power I is identity, I is also the smallest positive integer for which a phi to the power I is also identity. So the order of a phi is equal to I. Thus, order of a phi is also equal to I. And this small result we are going to record as a lemma, and this is the lemma. Let me just directly write the lemma. Lemma 283, let G be a group. If one wants to be more formal in how one presents these things, then one can also state the result first and then prove it. Herstein here, however, in many other places in this book, he has chosen to first present the demonstration as a discussion, and then whatever final result we get, he has chosen to state it afterwards, which is also nice. So let G be a group and phi is an automorphism of G. If the element A in G has order OA, which is greater than 0. This really means, in the context of this result, this means that we are assuming the condition that if A is an element whose order is a positive integer, that is, if A has finite order, then order of A phi is equal to order of A. Then A phi also has finite order and its order is also the same as the order of A. Okay, now after this there is a discussion about how one can use automorphisms to construct some groups from given groups. Say you are given a group and some particular type of automorphism of that group, you can use these two objects to construct another group. But unfortunately, the discussion that Herstein presents is so casual, it's casual to the point of becoming extremely confusing. Let me just write down exactly what Herstein has wrote in the book, and then we will just leave that thing like how we are going to write it. We will discuss a little bit about the situation and we won't leave it. We will actually prove what Herstein is claiming in this discussion, but in a slightly different manner. And after writing this thing down, I will also tell you what the problem here is. Automorphisms subgroups can be used this paragraph, of course, is just it. He is simply saying what he is going to do. Can be used as a means of constructing new groups from original groups. Okay, fine. How? Before explaining this abstractly, we consider a particular example. And the example is this. Let G be a cyclic group of order 7. Okay, so G is a cyclic group of order 7, that is G consists of, that means G will be generated by some element. Let that element be small a. G consists of a to the power I all a to the power I, where we assume that a to the power 7 is identity. Fine. the mapping phi which maps the element a to the power I to a to the power 2I can be as can be checked trivially is an automorphism of G. Of order 3. Okay, that is phi cube is the identity automorphism. Fine. Let X be a symbol which we formally subject to the following conditions. And these are the conditions. X cube is E, X inverse a to the power ix is equal to phi. Here again he writes functions on the left. I am not going to do that. I will consistently write functions on the right unless I am forced to write it in the usual way. And okay, so these are the conditions we are subjecting X to, and consider all formal symbols these symbols where I is, that is 3, no? So 0 or 1 or 2, and j varies from 0 to 5. No, 7, yes, so it will go up to 6. We declare that two such symbols are equal, that is xiaj is equal to xkal if and only if I is congruent to k modulo 3 and j is congruent to L modulo 7, we multiply these symbols using the rules. These are the rules. X cube, this we have already mentioned. This is equal to E, and X inverse AX is X square. For instance, there is an example has been given. What shall we get if we multiply say XA and XA square? According to these rules, it will be XAX A square, then AX from here is X cube. Is that what it is? No, I think, okay, sorry. This is not X square, this is A square. So AX is XA square. XA square A square. So this becomes X square A to the power 4. So like that, two such symbols can be multiplied. The reader can verify that one obtains in this way a non-abelian group of order 21. Now let me tell you my problem with this entire thing. Fine, G is a cyclic group of order 7. We know what a cyclic group of order 7 is. It's a group where these are the elements. Actually, these are not the elements. These are the elements. Okay, we consider these elements to be distinct and we define the binary operation like this. Say we have J, then we define it to be equal to A to the power this, where this exponent is the remainder that one obtains when one divides I plus j by 7. That is my definition of the binary operation. One can then show, in fact we have shown that this binary operation turns this set into a group and a finite abelian group. In that group, if you call this element A to the power 1 A, if you denote it by the symbol A, then you can see that A to the power 7 becomes equal to E. That is the most straightforward way of looking at the cyclic group of order 7. Here, however, Herstein says let G be a cyclic group of order 7, that is G consists of all a to the power I, where he does not say what I is. That is not a very big problem, where we assume a to the power 7 is equal to E. This is somewhat casual. This does not tell us what the binary operation is. Instead, it tells us that the generator of the cyclic group is A, or truly speaking, it's the element A to the power 1. It's the symbol A superfix 1, which is supposed to satisfy a relation like this. Now, can one really get this group only from this description? It turns out that one can, and in fact you will not get two different groups that satisfy these conditions. And this fact is not a trivial fact. It's coming from something known as presentation of groups. Group presentation theory, which says that if some symbols are given to you and a collection of some relations are given to you that those symbols are supposed to satisfy, then you can create in a very well defined way a group, a unique group for which those things are true. Herstein does not say anything about group presentations, but he uses it. That is my main concern about these things, the way it has been presented. Okay, fine. So we understand there is something called presentation of groups, and Herstein is using these things to mean precisely this. Okay, so if we don't use if we don't confuse ourselves into thinking what are we supposed to do in this situation, then at least for the cyclic group of order 7, this is what we are supposed to do, and we have already done that before. Okay, so this part we know, fine, there is no problem. And this mapping, there is no problem with this mapping also. An arbitrary element in this cyclic group is going to be a to the power I, and it has been mapped onto a to the power 2i, and one in fact can check trivially that this is an automorphism. It's not only a homomorphism, you can show it's an automorphism. The fact that it, besides being a homomorphism, this becomes a bijection depends on the fact that this 2 and this 7 are relatively prime. You will see why. If you want to start showing that this is an automorphism, you will see that relative primality plays a role. Okay, fine. So this is an automorphism of G of order 3, because this is an automorphism of this cyclic group of order 7. So it belongs to the automorphism group. So as an element in the automorphism group of G, phi will have its own order. That order is 3, which can also be verified easily. Okay, you apply any on any element in G phi 3 times in a row, you get the effect of the identity automorphism, that is it does not change. Okay, now after this the problem again starts from here to here. Here again Herstein is using presentation of groups. So what he does, he takes the symbol x, which we formally subject to the following conditions. So x is now a symbol, a is another symbol which we are having, which is coming from the cyclic group, and these two symbols are subject to these relations. So group presentation theory says that there is a group in which these things will be true. But the problem is, we are not so sure about the binary operation. That is the problem. You see, unless we know what the elements or the symbols in this group that Herstein is talking about are. The symbols are these. So our G now consists of symbols which look like this. Okay, fine, there is no problem with that per se, because in case of cyclic groups also we dealt with some symbols. We began the discussion, or we constructed a cyclic group by starting with a set of symbols, and then we defined a binary operation, and that is the only way we know, right? We get a set and we define a binary operation, we verify all the 4 axioms. If the 5th one is also true, then it becomes an abelian group, otherwise it's a non-abelian group. So that is the only thing we know in this book, and that's what we have to do. We don't have any other choice. We don't know what presentation of groups is or how it works. Fine. So the symbols look like this, where I can take these 3 values and J can take these 7 values. Okay. Now on that set of symbols, equality has been defined like this. There is no problem with this also. This notion of equality is well defined. It turns out to be an equivalence relation and all those things are there. Okay. But we multiply. So here Herstein tells us what the binary operation should be just by saying we multiply these symbols using these rules. Okay, so just by looking at these rules, it becomes extremely difficult to get an idea of what the binary operation in general looks like. You can of course use this we have in fact used this relation to find the final form of this product. If you operate on these 2 symbols using the binary operation what it is supposed to be, then using this relation you get this. But many questions are there in this type of reasoning. How am I writing these 2 symbols, the product of these 2 symbols equal to this? How do I know that A and X can be considered together? And what is in fact, what is the meaning of X inverse in the first place? That itself is not clear, because that those things take on meaning, or they become meaningful, they make sense only when presentation of groups is known. There is a theory. Okay, so this part the reader can verify that one obtains in this way a non-abelian group of order 21 can actually be verified without using presentation theory, but in a very tedious way. You consider all these 21 symbols, you form all the products, you see that the closure property is true, but then associativity, can you imagine how many different types of what I am trying to say is this. You have 3 symbols like this, xi, aj, x, suppose I prime, aj prime, and x I double prime, a j double prime. You form this product and you form the other product also, taking the first 2 together and then multiplying that with the third one. Do you realize how many different types of products have to be considered, and how tedious and awful the entire calculation will be? And every time you just have to use this rule, and then you see that all those things are the associative law turns out to be true. I am almost sure that by the time, even if you make up your mind that okay, no matter what, I am going to see that the associative law is true by going through all the details, I can almost guarantee that by the time you finish going through all the details to just show that the operation dictated by these rules is associative, you will lose all interest in this whole thing, because this is awfully long and this is the wrong way of doing things. So this part is really a very big problem in this way of presenting a group. See, that's why presentation of groups. Unless you have the theory, you cannot just leave it like this and say the reader can verify that one obtains in this way. It's almost impractical to verify it in this way. The better way is to, first of all, although it's difficult, to guess what the actual binary operation will be. That is, to guess what this will be, and then to see that in this general form you have to know what comes on this side. In this general form, yes, all the axioms are verified and this turns out to be a non-abelian group of order 21. Okay, and that's what we are going to do. But the problem still remains. What is the role of this automorphism of order 3 in all these things? Is it playing a role? That will not be apparent even in what we will do, but it will be apparent in what we do after that. You see, this is only one example, and then Herstein says that the general thing is done like this. So let us write what he writes after this. A non-abelian group of order 21. So the problem in this part is that Herstein uses presentation of groups, but he does not mention it. That is the problem. Generally, if G is a group, T and automorphism of G of order R. Keep in mind that G is any group. G may be an infinite group also, but the automorphism T of G has finite order and it has order R, which is some positive integer. And this is important, which is not an inner automorphism. If this is the situation, if we have a group and an automorphism T of it of order R, and the automorphism is not an inner automorphism, pick a symbol. So again he is using presentation of groups. Pick a symbol X and consider the elements x to the power I g. So just like here we considered x to the power I, this was any element in the cyclic group of order 7. Now that part is coming from our general group. X to the power I is just like that, just like before, where I is any integer and G is an element in G, because we are talking about symbols, so we have to subject them to some relations. I will say a little about what presentation of groups means, subject to first of all a criterion for two such symbols to be equal, that is xij equal to xj. He writes I prime, okay, fine, G prime if and only if I is congruent to I prime modulo R and G is equal to G prime, and X inverse G to the power Ix is equal to G T to the power, and there is a mistake in this equation in the text. The mistake is that this I think will not be here, because this means applying T on G I times. I think it will be this, which is an entirely different thing. We will see, okay, I can't remember at this moment. We will see when we go through all these things and actually show what he is saying, what the mathematician is saying. So for all I, this way, okay, this is an extremely vague way of saying everything. This way we obtain a larger group which Herstein is denoting like this. It shows that this group depends on the original group and the automorphism T. We will see later when we deal with this properly that the fact that T is not an inner automorphism makes this group non-abelian. Okay, we will see that it's always going to be non-abelian if we construct it this way. And something else is also true. G is, one can embed G inside this group. In other words, one can find an isomorphic copy of G inside this group. That is, there is a subgroup of this group that is isomorphic to G. And since we are considering isomorphic groups to be basically the same thing, just represented in a different way, in two different ways, so G can be thought of as itself a subgroup of this bigger group. That's why we are saying larger group. And as a subgroup of this group, G is normal in this. So if it's normal, we can form the corresponding quotient. This quotient, is isomorphic to the cyclic subgroup of this generated by T, because T is an isomorphism of G, so T is an element in this group, so it will generate a cyclic group. And that cyclic subgroup, because the order of T is R, that will just be the cyclic group of order R. We already know any two cyclic groups of the same order, any two finite cyclic groups of the same order are isomorphic in a very natural and trivial way. Which is equal to the cyclic group of order R. It will be of order R because the element that generates this cyclic group is of order R in this group. Now we will do these things, that is this non-abelian group of order 21 that we get from the cyclic group of order 7 and that particular automorphism of order 3 of it. And also this general case, we will deal with these things in the exercises. This has a name. It's called the semi-direct product of G and I think the cyclic group of order R. I'm not exactly sure. You will not find this term semi-direct product here in this book, but it's available elsewhere. This type of construction is semi-direct product and it is related to something else known as direct product, which we have already come across in vector spaces. Do you recall in vector spaces, if you are following those videos, we have defined direct sum of vector spaces, or rather subspaces, internal and external direct sum. Like that, one can also define internal and external products, direct product of, there we have subspaces, here we have normal subgroups of a group. Just like that, we have semi-direct product also, where say you have two subgroups n1 and n2 of a group. One of them is not necessarily normal. Then you can form a product of them which is like the direct product, but it's not. It's semi-direct product. One is normal and the other is not necessarily normal. Beyond this book, beyond Herstein's book, we will continue group theory, because this is only an introduction and the topics that we are getting here, so that's why this is known as the topics in algebra. These are just the beginnings of these things. There are many more things, things to be said about these topics. So we will continue our study. There we will see semi-direct product. Now after all these things, the last thing in this section is that for any cyclic group, whether finite or infinite, the author calculates the automorphism group. So this we will see in the next part. And in the next part, along with that, we will also start solving the exercises. So I end the video here itself. If you want to comment something on these things or something else regarding these things or anything else about mathematics, you can write in the comment section below, or you can mail me here. So that will be all for today in group theory. So see you in the next video. Until then, it's me Lucifer from a mathematical room. Have a nice night.